Hey everybody, welcome back to this second module. In this video, we're going to be going over the exploration that was covered in class for those of you that missed it. So I will go ahead and share my screen here. So for this second module, for this exploration, right, we're looking at this model of a DC residential, this DC model of a residential power distribution. And we are just using node voltage method, superposition, and Thevenin equivalent circuit, right? So we're going to be looking this week, we're looking at node voltage method, superposition, and Thevenin equivalent circuits. So that's just our topic for this week. And we've got this circuit that we're going to be analyzing. These two voltage sources have a total voltage of Vs. We've got these transmission line resistances R1, R2, and R3. And I forgot to draw them in, but we've got the low energy load resistors R4 and R5. And we've got the high energy load resistor R6. Right, so this circuit just kind of like models the power distribution around your house. R1, R2, and R3 are transmission line resistances, so they're relatively small. R4 and R5 are kind of like 120 volt appliances that you would plug directly into your wall sockets. And R6 would be like a 200 volt household appliance, like a washer, dryer, perhaps. So we're just going to be taking a look at this circuit, and we're going to look at the node voltages. And we're going to take this bottom left node is ground. All right, so we're going to say that this is 0 volts here. So we are starting off with the node voltage method. And I've listed out all the steps, how to go about using the node voltage method. And that's just in the background reading, but I'll just go ahead and take it through one step at a time here. All right, so it's a pretty straightforward method. You start off by labeling your ground. All right, you just choose some reference node arbitrarily to get your different node voltages with respect to that ground. And usually when we pick a ground, we pick one that is convenient for us, right? So by defining 0 volts to be this bottom left node, we're given that this junction between the two power supplies in R2 is Vs. So this voltage here is Vs. And we're also given that the voltage at this top power supply to be 2 Vs. Right, so we're going up through one power supply, so it's from 0 up to Vs, and then we're going from Vs up another Vs up to 2 Vs at that top left node. So that gives us the unknowns, or sorry, the what we know. And now what we want to do is go and label everything that we don't know. So we don't know one thing is this top right node, and we'll call that VA. We don't know this middle node junction between R2, R4, and R5. We'll call that VB. And we don't know this bottom node junction between R3, R5, and R6. We'll just call that VC. So those are all of our unknowns. And the next thing that we want to do is define our currents. And so what I usually like to do is have all the currents go from left to right and then recombine through ground. Right, so everything's recombining. So I3 is here, R2 we have a current going from VS to VB through R2, and then it's going down through R5, that's I5, and then we have up here at the top, we've got R1 going from left to right, to I1, R4 going from the top to the bottom, so I4, and R6 is going from top to bottom, I6. So we've labeled out all of our currents here. And again, these current directions are all arbitrary. What we're going to end up doing is write KCL equations for each of our unknown nodes. So first, let's just go ahead and write out all of these currents. So our currents, I1 is going to be this, right, so we start at 2VS, we're going down to VA. So right, the voltage between R1 is that 2VS minus VA. And we're going through R1. I2, follow that similar process. We're going from VS to VB divided by R2. Right, so we start at the base of our arrow, right, so VS, and then we go to the tip of the arrow, VB, and we take that difference, divide by the resistor that we're going through. And this is just, again, by Ohm's law. So I3 is going to be down here, so we're going from VC minus 0 to R3, right, minus ground. Then we have I4 to be VA minus VB divided by R4. We've got I5 to be VB minus VC by R5. And we've got I6 to be VA minus VC by R6. Okay, so now, right, so we started off, we labeled our reference, and then from our reference, we figured out what we do know, right? So we know that this is VS, this is 2VS, and then we label the nodes that we don't know, VA, VB, and VC, and then we label all the currents that are going through each element, except the voltage sources, right? Because we know we don't really care about these. These are all given to us. We want to figure out these currents. We want to write out these currents in terms of the node voltages. Okay. So our next step is to take KCL. We'll have a KCL equation for each node, each unknown node, right? So we start off, we take KCL at node A. And we've got I1 going in, I4 and I6 coming out. And so I1, just by KCL, what goes in must come out. So we can add up the currents going in, subtract off the ones coming out, and that should sum to 0. So I1 minus I4 minus I6 equals 0. And then we expand this out, right? So maybe I won't go this way. So then that gives us 2VS minus VA by R1 minus VA minus VB by R4 minus VA minus VC by R6. That'll be 0. And what we want to do from here is extract out all the voltages. So we take VS, we've got 2 by V1, 2 by R1 VS, and then we want to add VA. How many VAs do we have? We've got -1 by R1, -1 by R4, -1 by R6. 1, 4, 6. And then we take our VB terms. So we've got +1 by R4. And we collect our VC terms, and we have +1 by R6. And that all will equal 0. So this is our first equation here. Put that in a blue box. All right, so we're gonna end up with this system of equations. So we've got these three unknown nodes, and we're writing out the KVL equations for each node so that we can get a system of equations and solve for the three unknowns. And so our next step then is to do a KCL at B. So at node B, we've got I4 going in, I2 going in, and I5 coming out. We get I2 plus I4 minus I5 equal to 0. I2, yep. So we expand this out. We got Vs minus Vb by R2 plus Va minus Vb by R4 minus Vb minus Vc by R5. And that'll sum to 0. So we extract out all of our terms again. We get Vs 1 by R2. We've got Va. How many VAs do we have? We've got 1 by R4. We'd get Vb. How many Vbs do we have? Negative 1 by R2, negative 1 by R4, negative 1 by R5. 1 R2, R4, R5. And then how many VCs do we have? Well, we've got 1 by R5. And all of this will again sum to 0. So here's our second equation. Cool. And then what we want to do is finally get our last equation. So we got KCL at node C, and we can take a look back here. So we've got 5 and 6 going in, 3 coming out. That's I5 plus I6 minus I3 equals 0. We look back at our equations up here. So we got VB minus VC by R5. We've got VA minus VC by R6. And we've got minus VC by R3. And that should be 0. So we collect our terms. In this case, let me clean this up. In this case, we don't have any VS terms. We have VA, we got 1 by R6 VA. We've got 1 by R5 VB, and we've got minus 1 by R3, minus 1 by R5, minus 1 by R6 VCs. And that again will all sum to 0. And now, right, so we take our system of, we take our three equations, we convert them into matrix form. So let's just recombine everything here. I can do that. So let's take our first equation, copy it down here, just so that we can have it for reference. This is supposed to be 1. That's equal to 0. Did that copy over correctly? Yeah, okay, we're good. And then we take our last one here. So I just copied them down here for quick reference. So now we have our three equations. And this is our system that we want to solve, and you're welcome to use any kind of numerical solver that you like, but let me just show you kind of how to do it in MATLAB. So let's just put this all into matrix form now, right? So looking at the first equation, I'm going to move all of these unknown terms over to the right-hand side. I'm going to add them all over, or subtract them all over, rather. And that will give us 1 by R1 plus 1 by R4 plus 1 by R6. That's how many VAs we have. We've got negative 1 by R4 VBs, and we've got negative 1 by R6 VCs. And so we're going to end up writing this into a matrix form. We've got VA, VB, VC. And that's going to be equal to just this 2VS divided by R1. So 2VS divided by R1. And that's our first equation there. Then looking at the second equation, right, we're going to be setting everything equal to VS divided by R2. And we've got 1 by R4, right? I'm going to move all these over to the other side of the equal sign. So we've got 1 by R4. We've got negative 1 by R4 because we moved it over. We've got 1 by R2 plus 1 by R4 plus 1 by R5. Right, and I could have chosen to move VS to the other side, but yeah, I mean, you guys know how to solve these systems of linear equations by now, I hope. And then lastly, I just move everything to the other side to keep it consistent here. So minus 1 by R5 and 1 by R3 plus 1 by R5 plus 1 by R6. And again, in this last term, last equation, we don't have any VS terms, so that's going to sum up to 0. So now we take this, right, and we're going to let R, so we have this set of resistors. I think I said R1 is 3.3 ohm, R2 is 10 ohm. Let me just open the experiment up here, just so that I can double check these values. Yeah, so R2 is 10 ohm, R3 is also 3.3 ohm. Now we've got R4 to be 47 ohm, R5 to be 120 ohm, R6 to be 100 ohm, and we've got VS to be 2 volts for our experiment. And so let's go ahead and do this in MATLAB then. So I'm going to open up my desktop here. I think my desktop is now sharing. So yeah, I think my desktop is now sharing. So I'm going to go ahead, I'm here in MATLAB now, and I'm going to, let me just make sure actually. Okay, yeah, that is what it looks like when it's sharing, I guess. So I'm going to take my resistors and I'm just going to define it as 3.3, 10, 3.3, 47, 120, and 100. And so I've got this vector of resistor values that I can take out. I'm going to take VS to be 2. And actually, I guess before we talk about this, we'll just go into a little bit of matrix theory. So let's go back to the iPad here. There we go. So looking at this, we usually call this matrix on the left the conductance matrix, and conductance is the inverse of resistance. And so we've got a matrix of all these conductances. If resistance is measured in ohms, conductance is measured in mhos, and it's usually this upside down omega symbol that we use to represent it, but that's not super important. So we're going to call that our conductance matrix G. I'll call this unknown vector x, and this is like our known, right, our solution. I'll just call it b. So we're going to take g, we've got g times x is equal to b, and assuming that g is invertible, we take x is going to be g inverse times b by our wonderful properties of linear algebra. And in MATLAB, right, we can take this x equals g, there's this built-in function called inv, where it takes the inverse of a matrix, inv g, and then times b. And so this is in MATLAB for those that want to use it. So now let's go back to our MATLAB. So here I am back in the command prompt. I've stored R and VS into my workspace. What I want to do now is define G. And based on what I've got here, so G was 1 by R1 plus 1 by R4 plus 1 by R6. And then to get the next entry, right, the next row, the next column, right, so we stick in this first row, but go into the next column, so minus 1 by R4. To go to the next entry, you just do a space, and minus 1 by R6. And to go to the next row, right, so we're going now to the second row, we do a semicolon. We do negative 1 by R4. Next entry, 1 by R2 plus 1 by R4 plus 1 by R5 minus 1 by R5. And the last row, negative 1 by R6, and then a negative 1 by R5, and then 1 by R3 plus 1 by R5 plus 1 by R6. And that will give us the matrix G into our workspace. So we can just double click on this to see what it looks like. Yeah, it's a 3 by 3. Okay, and then we want to define our vector B. So B, again, was this 2 times VS divided by R1. And then in the next row, we've got VS divided by R2. And in the last row, we've got 0. Okay, so now we've defined all of our necessary variables, and we can take x, right? Our unknown vector is going to be inv g times b. I had a little typo there but yeah, so this is your list of expected values for VA, VB, and VC. So I'll just go back again to iPad here. Oh, there we go. So I accidentally wrote inv g times g for some reason here. It's times b, right? And that gives us this column vector of the values, the unknown values. So VA in our case is 3.7693. VB, wow, what kind of 7 is that? 7693, VB is 2.1730, and VC is 0.1736 in our case here. And yeah, so that's the first problem for the exploration. And what you should find, right? So we then go into superposition, and what we should find by superposition, we look at the individual responses due to each source. So I'm just going to draw out the circuit again for us here. So by superposition, we've got two sources, and VA, VB, and VC. By superposition, we should be able to look at the individual responses, right? So when we set a voltage source, we've got our 2 voltage source, we set it to 0 volts. That's the same as shorting them out. So we analyze, we say VA is going to be VA1 plus VA2, where VA1 is the response due to maybe say the top voltage source, and VA2 is the response due to the bottom voltage source. And similarly, VB due to the top, due to the bottom, and VC due to the top and then due to the bottom. So what we end up having, right, we analyze first due to the top, right, so we short out the other one, and we've got our VA1, VB1, VC1, and then we look at the responses due to just the bottom source. And so then we've got VA2, VB2, and VC2. And this was kind of an interesting exercise, because when we get to this point of looking for the 3 different node voltages, right, it just turns out that after applying the superposition method, we probably have to do node voltage for this circuit and node voltage again for this circuit, right? Unless you wanted to, you could equivalently determine the equivalent resistance for both of these, right? So find the equivalent resistance, find the current going through, determine all the voltages everywhere, and you could go about it that way, right? And then I forgot, these are the node voltages with respect to this ground. Right, so the ground will always be here. Right, so this was kind of just a cruel example of, in this case, yeah, I mean, it would just be better to start off with the node voltage method. But again, you should be able to sum these responses and find that they are in fact the same. You get the same result as just doing node voltage the first time. And so the last part, I'm not going to do node voltage 2 more times here. I'll let you guys do that for fun. The last thing we want to talk about is Thevenin. And for the Thevenin equivalent circuit, we look at the voltage across the load. So we're calling R6 to be the load. I'm going to draw it again here. Let's pull this one. So we say that R6, and so R6 is our load, and we find the Thevenin resistance, right? So Thevenin says that we can simplify any linear circuit, any linear network, right? So any linear network means just, so we've got voltage sources and resistors, and these resistors have a current voltage characteristic of V divided by R, right? So these are linear graphs, linear in voltage and linear in current. So Thevenin says we can take this, well, first off, we say R6 is the load. So let's just go ahead and remove that. And you can choose any point to be the load, as long as the rest of the circuit, the rest of the network is linear. Right, so this is our network, and we're going to simplify this. So the first thing that we want to do Right, so we're gonna put it into, we're gonna have some V Thevenin in series with R Thevenin, the Thevenin resistance and Thevenin voltage. And it's again across this load here, so we call that A and B. And R Thevenin is the equivalent resistance seen by the load by deactivating all the sources. So by deactivating the voltage sources, we replace them with a short, and we're looking at this equivalent resistance. Right, so we're going to collapse this network, R1, R2, R3, R4, and R5. We collapse that network, figure out what the Thevenin resistance is, and V Thevenin is going to be the voltage across A and B. Well, I guess we'll call this A and C. Across A and C, just if the circuit were operating normally. Which in our case, from step one, we've already found VA and VC. So V Thevenin, right, so R Thevenin is the equivalent resistance here. And V Thevenin is VA minus VC, right? The difference between A and C. And I think that's all I wanted to talk about as far as the exploration is concerned. So thanks for tuning in. Sorry that it took a while, but I hope it helps you, you know, in lecture. Hope it helps connect some of the dots during lecture. But I'll see you guys in the next one. Thanks.